It is interesting to work with the carbonate system, the carbonic acid system, but what we really want to understand is the interaction with the lithosphere and as a geologist with the limestone. And to do that, you need to add a very important component, which is a cation. Now you are able to know if you can produce carbonate ion, for example, and carbonate is very important for the precipitation of limestone. But if you don't have any calcium or magnesium or other cation, you will not be able to precipitate a mineral. So, in order to do that, you need to have a system where you're adding calcium. And to do the similar calculation and playing with those different equations, but with the notion that you, in addition to in your system, you don't have only DIC, but you have DIC plus a cation, in this case Ca2+. Let's write in another color here. So, what are the equations you can play with to solve various problems? For example, what is the pH of the solution in equilibrium with calcium carbonate and the atmosphere, for example? You want to be able to calculate that. You need to have a set of equations to work with and to play with to be able to solve as a function of the question you have. So the first equation, pretty simple, is the expression of the carbonic acid as a function of your Henry's constant and the pCO2. This is from the first equation of the mass balance equation of the dissolution of CO2 into the water. The second one is, we know that again is the Ka1 value, which is equal to the H plus times the bicarbonate divided by the carbonic acid. This is the second equation. The third one we are familiar with too, which is a Ka2, H plus times the carbonate, in this case divided by the bicarbonate. Now we'll add two more equations to deal with this system because you're adding calcium. First is the precipitation and dissolution of calcium. And the simple way to express that is calcium carbonate, which is CaCO3, is giving you a calcium plus a carbonate. And this reaction here have a what we call Ksp with a constant of solubility for, in our case, the calcium carbonate minerals. And this we know that it is equal to Ca2 plus the product times the concentration of 2 minus divided by the concentration of CaCO3. And we know that this is a solid, this is aqueous, and this is aqueous. So this is equal to 1. So the Ksp equal the concentration of calcium times the concentration of carbonate. This is our fourth equation to play with. A fifth equation is what we call the charge balance. A solution has to be balanced with the charge, cannot have a positive and negative charge, can have free electron flying around or free H plus flying around. When you have a neutral pH, you have the same amount of charge in your system. If you're adding a substance in it, it will always dissociate it in one negative charge and one positive charge that will basically have a balanced charge at the end. So what is the positive versus the negative charge in our system is m of the H plus, the m is basically the number of charge coming from an element, and it is a mole of charge. If I'm taking an example, H plus, if I have a concentration of H plus of 1 mole of 1 molar per liter, that means I have exactly 1 mole per liter of charge, of positive charge. If I have calcium in solution and I have 1 mole of calcium, that means I have 2 charge for 1 mole of calcium. That means I will have 2 mole per liter of positive charge in this case. Okay? So if you look at the mole of charge related to one element, you need to multiply by the number of charge of the cation or the anion. So in this case, you have the mole of H plus 2 times the molar concentration of calcium equal, for the negative charge, the M of the HCO3 minus, the bicarbonate, plus twice the mole of CO3 2 minus, because it's a 2 charge, 2 negative charge, ion, so you need to multiply by 2, plus number of mole of OH minus. So you have your elements here, you have H plus, you have the OH, that with balance, okay, and you will have your calcium and your carbonate and your bicarbonate together. So this has to be balanced. So the sum of all those charges has to be 0. So this is your fifth equation. So now let's combine those different equations to, for example, express the pH of a solution in equilibrium with calcium carbonate. So the first, you're going to take the simplification of the near neutral pH. Why is this? When you have a charge balance here, missing an E here. Of course, this is a generic global equation, but most of the natural system will have a pH close to neutral. So you won't have a lot of H plus in solution, nor a lot of OH, because they will be balanced. The pH is around 7, so you will have as many H plus as OH minus. Okay? And if, because you are neutral in the pH, you won't also have a lot of carbonate, because you know now that carbonate start to be abundant when you're going into higher pH, when you're passing the pKa of 10.3 for fresh water, a bit lower for marine water, but clearly higher than 9. At pH between 7 and 8, you mostly have bicarbonate. So you can simplify this charge balance equation by just using those two members here. This simplification here will give you that the number 2, better with white, 2 mole of charge from the calcium will equal 1 mole of HCO3 minus. The next step is taking the equation 4, the equation for the dissolution of the calcium carbonate, equal to the concentration of calcium times the concentration of carbonate, and you can express this carbonate here using equation 3. You have the carbonate here, and you're expressing this carbonate as, in this case, Ka2 times the concentration of bicarbonate divided by H plus. So if I'm substituting this here, I will have your calcium, and this is going to be equal to Ka2 times the concentration of bicarbonate divided by the concentration of H plus. And now what you're going to do is replace what you just calculated for calcium in this equation here. That means what you're going to have is KSP, I'm missing a P here, equal the concentration of HCO3 minus divided by 2 times Ka2 HCO3 minus divided by H plus. So now what you don't know is the concentration of bicarbonate. So you need to substitute this and to express bicarbonate as a function of something you know. So to do that, you're going to use equation 1 and 2, because you have substituting, that we already did that before, the carbonic acid with this equation here. So in this case, you can express the bicarbonate as a function of Ka1 times KCO2 times the PCO2 divided by the pH. And you're substituting that in the next equation, which is here, and that will give you a totally different one, which is, in this case, KSP equal HCO3 minus square times K2 divided by 2H plus. What I did here is just rearrange this here. I multiply this by this, which is giving you this, and then it will give you only that at the end. And then now I'm substituting our value that we have here with HCO3 minus equal Ka1 times KCO2 times PCO2 divided by H plus. So this will be put into here and will give you this nice little solution at the end, when KSP equal Ka1 times KCO2 times the PCO2 divided by H plus square times Ka2 divided by 2H plus. Again, this is the same equation here. You're finding back, and this is your PCO2, and you're replacing this bicarbonate by a set of constant and a pH that you can actually know. Not the pH, the concentration of H plus. And the next step here is to solve for pH if you want. If you want to know what is the pH of a solution in equilibrium with calcium carbonate. That means in our example we have KSP equal Ka1 squared times KCO2 squared times PCO2 squared divided by H2 squared times Ka2 divided by 2H plus. That means that in our case H plus to the power of 3 equal Ka1 squared times KCO2 squared times PCO2 squared times Ka2 divided by KSP. And if you want to have the solution for H plus, you just have to take the square root of this number. I read that here. So this is your solution. You're taking minus the log of that, and you have your pH as a function again of constant, all constant, and some known value that is a PCO2 that can be expressed or can be used as a constant in this case. You will have some example, or one example in the assignment where I ask you to calculate the pH of a solution. So you're going to do exactly this for this example.